definition for DTMC. This definition holds for finite as well as countable states. Maybe I should say DTMC with stationary distribution pi I is said to be reversible if Pij star derived above is equal to Pij for all ij belongs to S, i.e. it is the same as saying pi I Pij is equal to pi j Pji for all ij belongs to S. Okay. So, if pi I Pij is equal to pi j Pji for all ij belongs to S, then we will have Pij star is equal to Pij, right, which means that the transition probability from I to j in the forward chain is the same as the transition probability from I to j in the reverse chain for every ij, right. Such a Markov chain is said to be reversible. Okay. So, what this is saying, so if you look at that picture, this is I, this is j. So, you have some, this is the detailed balance, okay. This is Pij, Pji. So, for any two pairs of states, the rate of transition from I to j is the same as the rate of transition from j to I. For any two ij, it could be I to k, j to k, k to l, any two pairs of states in the Markov chain, this should hold. Okay, this is again the local balance, or sometimes known as detailed balance, local balance equations or detailed balance equations. So, reversibility is basically local balance holding for any two pairs of states. It is defined in terms of local balance. Okay. Excellent. So, that is what reversibility is. So, if pi j Pji is equal to pi I Pij, then we know that the forward running Markov chain and the reverse running Markov chain are statistically completely indistinguishable, right. So, if somebody shows you a video tape of transitions going forward, let us say I go from state I, j, k, blah 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 in the forward chain and I run it in reverse, the statistical properties will be identical. So, you will not be able to tell whether the tape is running forward or tape is running backward for a reversible Markov chain. Okay. In general, you can. Okay. So, in general, for if you take some Markov chain, the reverse transition probabilities will be like Pij star, which are derived here. Okay. It so happens that for a reversible Markov chains, by definition, Pij star is equal to Pij, and you will not be able to tell by looking at the the statistics of transitions. You will not be able to tell whether the time is running in this direction or whether it is running in this direction. All right. Now, clearly, this local balance equation is satisfied by birth-death chains, right. So, what is, we can straight away write down all birth-death chains with a stationary distribution are reversible. Okay. So, if just from our previous discussion, we know that local balance is satisfied between any two pairs of states in birth-death chains, right. So, as long as the birth-death chain has a stationary distribution, has a pi, all right, which means that the birth-death chain is positive recurrent. So, we are just saying that all positive recurrent birth-death chains are reversible. Okay. So, if you look at an evolution in the forward time of a birth-death chain or in the reverse time, you will not be able to tell the difference statistically. Okay. Now, it looks like to establish, so how do you establish that a Markov chain is reversible or otherwise? You need to verify whether pi I Pij is equal to pi j Pji, right, for every two pairs of states I and j. So, it looks like we are in an unhappy situation where you need to first figure out the stationary distribution pi I before you can even tell whether the Markov chain is reversible or not, right. It turns out that this is not necessary. Okay. There is a theorem that says that if you manage to guess some probabilities pi I which satisfies local balance, then these pi i's are in fact your stationary probabilities, stationary distributions, and that the underlying Markov chain is positive recurrent and reversible, all right. Suppose that an irreducible DTMC has transition probabilities Pij, and suppose pi I are a set of positive numbers summing to 1 satisfying local balance, i.e. pi I Pij is equal to pi j Pji for all ij in S. Then 3 things come for free. Pi I are the, so pi I, maybe I say pi is the stationary distribution of the DTMC the DTMC is positive recurrent and reversible. Okay. So, this theorem is saying that, so pi I you somehow find some pi i's which sum to 1, all right, satisfying local balance. So, you are given Pij, the transition probabilities, and you somehow manage to guess these pi i's which are a probability distribution such that local balance is satisfied between any 2 pairs of states. So, you do not know this what these pi i's are, you just manage to guess some numbers which sum to 1 and satisfying local balance. Then what happens is this pi I are in fact the stationary distribution of the Markov chain. These pi i's are unique and this is the stationary distribution, and then the Markov chain is positive recurrent and reversible. Okay. So, you get all of this for free. Okay. So, if you somehow manage to guess these pi i's by looking at the structure of your chain or looking at your Pij's, then you immediately get reversibility and you have automatically found out the stationary distribution. Okay. So, proving this is actually easy. So, since you have pi I Pij is equal to pi j Pji, okay. So, you know that they sum to 1, right. So, you just sum this over j, okay. So, this is true for all ij. So, I am just summing both sides over j. So, if you look at the left hand side, sum over, so pi I this is independent, this has nothing to do with the j at all, right. So, I can pull that out of summation, and then I have sum over Pij which is simply 1, right. Sum over j Pij is 1. So, I get pi I is equal to sum over pi j Pji. Now, what is that, right? This is global balance, right. So, what have we shown, right? Local balance automatically implies global balance, right. because sum over pi I is equal to 1, it is already given, they sum to 1, and we are looking at sum over j of the local balance equations. I have pi I is equal to sum over j pi j p j I, right. So, I am able to recover global balance from local balance, which means that local balance equations imply global balance. Okay. Converse is not true. If global balance is satisfied, it is absolutely not the case that local balance should be satisfied, not at all the case. In that case, if you satisfy global balance, it does not imply local balance. If it did, then all Markov chains would be reversible, that is absolutely not true. Okay. But local balance always implies global balance. Okay. And since we have these pi i's which satisfy local balance and sum over pi I is equal to 1, local balance imply global balance. So, these pi I satisfy sum over pi I equal to 1 and global balance. Okay. And we already know that if pi I satisfy global balance, then these pi i's are unique and the underlying Markov chain is positive recurrent, alright, and these pi i's are the unique stationary distribution of the Markov chain, right. So, this implies DTMC is positive recurrent. And it also implies that pi I is the stationary distribution. Okay. So, the pi I that you manage to guess which satisfies local balance and normalization automatically becomes the stationary distribution of the Markov chain. Now that pi I have the interpretation of stationary distribution, you go back to local balance, right, that implies reversibility, right. Now then local balance, so this implies reversibility also, because now pi i's have the interpretation of this steady state stationary distribution, and then this pi I p I j is equal to pi j p j I is satisfied for any two pairs of states, and therefore the Markov chain is reversible. Okay. So, this is a very nice elegant theorem which says that if you somehow manage to find these pi i's which are normalized and satisfy local balance, then these pi i's are these steady state probabilities and that the underlying Markov chain is positive recurrent and reversible. Okay. This is a very useful theorem. Okay. There is one more related theorem which there is a theorem, maybe I should not spend too much time on this. So, if you find there is theorem 6.5.3 in Gallagher which says that if you manage to find any pi i's and some other pji star which satisfy pji star is equal to pji star is equal to pi I p I j over pi j, then the Markov chain is such that it is positive recurrent, pi i's are the steady state probabilities, and pji star that you found are the transition probabilities of the reverse Markov chain. That also can be proven. Okay. But I think this theorem is much more useful, although the next theorem I stated is more general, I think this is probably more useful. Okay. So, this pi I p I j is equal to pi j p j I is quite useful. Now, if you have a reverse, so there are some quick tests for reversibility that you can make, right. So, suppose Pij greater than 0, but Pji equals 0. Okay. So, you can go from I to j. So, there is a k and all that. Okay. So, you can go from I to j, but you cannot go from j to I. Okay. Let us say there is some Markov chain like that, right. This Markov chain can never be reversible. Why? Because pi j p j I will never be equal to pi I p j j. Intuitively, the forward chain you will see transitions from I to j, okay. But in the reverse chain, okay, you will never find transitions from I to j. You will only see transitions from j to I, right, in the reverse chain, right, because in the forward chain you will have transitions like I, j, k and all that, but in the reverse chain you will never be able to find transitions from I to j, you will always find transition from j to I, right, because in reverse chain transition from I to j would mean a forward transition from j to I, and that is not possible because Pji is 0, right. So, if you have a situation where Pij is greater than 0, but Pji is 0, then you straight away know that the Markov chain is not reversible, alright. And similarly, for example, if it so happens that P, let us say for 3 states I j k, if it so happens that Pji Pik Pkj is not equal to the opposite Pjk Pki Pij. Suppose this is the case, right. So, what am I saying? So, this is Ijk. So, Pj, so probability of going from j to I and then I to k and k to j, okay. If you are multiplying all these probabilities, if that is, this product is not the same as Pjk, Pki, Pij, okay. If this product on the left is not equal to product on the right, then this chain can never be reversible, because the probability of going from I to j to k is different from the probability of going. So, this probability in going the cycle in one direction is different from going in the other direction, alright. So, the forward statistics and the reverse statistics will not be the same, right, in which case you can tell the difference. So, the Markov chain cannot be reversible. So, indeed if it were reversible, right, indeed if it were reversible, you have that pi I should be equal to pi j Pji over Pij, right. That is equal to, if it were reversible, it should satisfy pi k Pki over Pik, right. This should be true. If the chain were reversible, this should be true, which implies pi j Pji Pik is equal to pi k Pki Pij, right. So, this should be true, and also we should have pi j Pjk equal to pi k Pkj, alright. So, if you divide these two equations, so these two equations have to hold if the chain were reversible, and if you divide this equation, you will get Pji Pik Pkj equals Pjk Pki Pij, okay. So, what this is saying is that if you product the probabilities going that way and the probabilities going that way, right, they should be equal. This should be true for all, Ijk, right. Even if for one triple Ijk, if this were not true, then the chain will not be reversible. Similarly, you can show this for cycles of length 4, cycles of length 5. For any cycle of length 4, you should have the probability of going in this way is equal to probability of going the other way, right. Even if there is some cycle where the probability of going in this way is not equal to the going in the opposite way, then the chain cannot be reversible, okay. So, it is necessary. What is surprising So, for every cycle a reversibility would so it is necessary that the product of probabilities this way should be equal to the product of probabilities in the opposite direction, right. But it turns out that it is also sufficient if for every cycle, if the product of probabilities going one way is equal to the product of going the other way for every cycle, then you can show that the chain is in fact reversible. Okay, that is a more non-trivial result, but it turns out that that it's both necessary and sufficient. Okay, that's anyway just an aside. So, before I conclude this discussion, I want to talk about reversibility and periodicity. The question is, can a periodic DTMC be reversible? Okay, so far we have discussed periodicity long ago, okay, which means that returns to the same state happen only in multiples of a certain d, right. If that is the case, then we say that the state is periodic with period d where d is greater than 1, right. Now, can a periodic DTMC be reversible? All right. Remember that for a periodic DTMC, let us say of period d, right, I can subdivide the states, you know, into these classes, okay, where all the transitions happen from S0 to S1, S1 to S2 dot and then SD minus 1 to S0, right. You can always subdivide the states into these subclasses where all the transitions go from S0 to S1, S1 to S2, S2 to S3, SD minus 1 to S0, okay, all transitions go this way. Now, imagine what reversibility means, right. You cannot have a, see, then it is not possible to go from S0 to SD minus 1, SD minus 1 to SD minus 2 and so on, right, because all transitions only go this way. If I run the time in reverse, all the transitions will go in the reverse direction, right, and therefore the statistics will not be the same, right. So, in this picture it appears that a periodic Markov chain cannot be reversible except if d is equal to 2. If d is equal to 2, what happens? You will have only a partition of 2, that is S0, that is S1, right. So, all transitions go from S0 to S1 and S1 to S0. So, you will get S0, S1, S0, S1, S0, S1. Reverse chain you will get S1, S0, S1, S0, which is the same, it is exactly the same sequence, right. So, the answer is a periodic DTMC can be reversible only if the period is 2, okay. This argument is enough to show the answer, a periodic DTMC with period d greater than 2 cannot be reversible due to the argument that we just made, right, because the sequence S1, S0, S1, S2 will occur in the reverse direction and you can tell the difference, all right. Okay, so that with that I will stop the discussion on reversibility.